Swayam Prabha. Digital India. Educated India.
Hello everyone. So, in the last class I have discussed about different boring techniques, then the test speed and then the SPT, standard penetration test, and I was discussing about the different corrections that we have to apply on SPT value. So, as per IS code that we have to apply the overburden pressure and the latency correction. So, this overburden pressure correction is applicable for granular soil and the latency correction applicable for saturated fine sand and the silt. So, in that sense, if the soil is clay, then no corrections are required. So, that means corrections are required granular soil or silty soil. Okay? And I have discussed why this overburden pressure correction is required and latency correction is required. So, as if I have discussed that if effective overburden pressure is less than 10 ton per meter square, then the corrected N value should be more than the measured N value because of the overburden pressure correction, and if the effective overburden pressure is more than 10 ton per meter square, then corrected N value is less than the measured N value, and even after application of the latency correction, your N value will also decrease. But if the N dash value is greater than 15, then only we will apply the latency correction, and why it is, then I have also discussed. But in as per the ASTM, that American Society for Testing and Materials, they have proposed 5 corrections. Okay? So, what are those 5 corrections? So, this Cn is the correction due to effective overburden pressure, and this is the expression. So, in IS code we use the chart. From that chart we can get the Cn value. This is the chart, this is the effective overburden pressure, and this is the correction factor Cn that you will get from this chart. And but here I will get the Cn value from this equation, where P0 is effective overburden pressure, which is in kPa. And then in addition to that, we have to apply 4 other correction, but here dilatory correction is not required. This is not recommended as per ASTM. So, these corrections are the hammer efficiency correction, drill dot correction, sampler correction, and borehole diameter corrections. Okay? So, these corrections also we have to apply. Now, and here N means the measured one, N dash means the corrected, and 70. What is 70? Because such 70 is not mentioned as per IS code, but I will discuss what is 70. So, I will go for first what is 70 part. So, the first correction is that eta 1, this is eta 1 the hammer efficiency correction, then eta 2, eta 3, eta 4 are the other corrections. Now, what is hammer efficiency correction? This hammer efficiency corrections is the ratio of ER and ERB. What is ER? ER means, because we know that these our for standard penetration test, this is the hammer weight and this hammer height of fall is this much. So, we know there is a actual there is a standard energy that we are applying into the during the blows. Okay? So, that means we know that this is my height, this is the weight. So, this will be the free fall. So, that means everything is standard. So, we will based on that we will get what will be the input energy you will apply during your test. But in actual case, there may be some energy loss, because everything may not be in proper shape. Okay? So, that is why during the test the input energy and the actual energy that you are applying may not be the same. So, that is the ratio is ER, that means the actual energy that you are applying to a sampler and the input energy that you are supposed to apply. So, that is your ER. And what is ERB? ERB is a standard energy. What is standard energy? Because in a site you are doing say 1000 penetration test, and it may not be possible to conduct all the test in a same energy. For example, that sometimes your hammer energy may be 70%, sometimes 70% with respect to the energy that you are supposed to apply, because as I mentioned, your energy will be less than 100% because of some energy losses. That may be your instrument problem, or that may be your manual error. So, that means or the instrument that you are using, that depending upon that your applied energy may not be 100%. But in all the tests you cannot do a particular energy, because some tests you may do with 60%, some may 70%, some may 80%. So, at different energy, but when you represent them in your report, it is very difficult to see that someone is 80, someone one is 70, then 60. So, it is better to represent them in a standard energy. So, that standard energy is ERB. So, that your standard hammer efficiency is ER you will get from this equation, and then ERB. So, depending upon which type of hammer you are using, so ER is available. So, for different types of hammer, this ER value is given. This is 45 to 67%, and then 70 to 80, 80 to 100. Okay? So, that means this is your different hammer, your ER value you will get. So, that means ER value will get which hammer you are using based on that. Now, suppose if your ER is 80 and you want to express that N value which you are measure by applying ER is equal to 80 to a standard energy ratio of 70. For example, that means you are applying a 80% energy, but now you want to express them in 70% energy. So, that means you applied more energy, but you want to express them in less energy. So, definitely when you want to express them in less energy, your measured N value will increase, because during the measurement you applied more energy. Now, you want to express them in the less energy. If your energy is less, that means there will be more N value. So, that is why your correction factor will be more than 1. So, that is there 80 by 70, that will be 1.14. That means ER is 80, ERB is 70. So, this is 1.14. If it is reverse, that means you are applying the 80%, 70% energy and you want to express them in 80%, then your corrected N value will be less compared to the measured N value. So, in such case your correction factor will be less than 1. So, this is the concept of 70, 80. So, that 70 that I have discussed, that 70, this is the standard energy by which we will represent all the SPT values. We may have done the test at different energies, but we will represent them with a standard energy, that is 70. Okay. And then we have to apply the corrections for the rod length, and that is eta 2. If the rod length is less than 10 meter, then I will get a very high N value. So, that is why it is recommended. So, you always use the rod length more than 10 meter or equal to that. So, that means this is the if it is more than 10 meter, then no corrections are required, then because the eta 2 is 1. But if you use the less than 10, because it is not always possible to use more than 10 meters. So, if you use the less than 10, then you have to apply the corrections, and as I mentioned, the less than 10 will give you higher n value. So, the correction factor will be less than 1. So, this is the correction factor for different rod length correction factors. Similarly, for we can use the different sampler. So, few sampler may be liner, few may be without liner. So, that if it is without liner, then correction factor is 1, but if it is with liner, then because with liner the dense sand and the loose sand, then these are the correction factor. Then if borehole diameter also influence the n value, if this is the borehole diameter, corresponding correction factor. So, we have to apply all the correction factors, and then finally, we will get the corrected n value. So, this is one particular example, that if your n value is 21, rod length is 30. So, if it is 13 means your correction factor will be 1, because this is greater than 10. Then hole diameter 100, P0 bar is 200 kPa, ER is 80, and it is a loose sand and without liner, and we want to represent them in 70 and 60, what would be the value. So, then all these values I will get, because this is ERB is 70 and ER is 80. So, this is eta 1 is 1.14, eta 2 is 1, eta 3, because this is eta 3 is without liner. So, it is 1. Then borehole diameter is 100 millimeter. So, this is 100 millimeter, again it is 1. It is 60 to 120 millimeter is 1. So, this is also 1, and then we have a P0 bar is 200. So, Cn value I will get from this equation. So, this is 0.69. So, overall n dash 70 is 17, and then we can get the n dash 60 also, that will be, if 70 is 17, and definitely for if I go to lower energy level, then n value should increase. So, that is 20. So, this is the different corrections for as per IS code and the ASTM. Now, based on the n value, we can identify which type of soil it is, and we can get the Cu value or the phi value, Cu value in the undrained cohesion. So, this is by using different correlations. So, this is one correlation that I am showing you. You will get such correlations in number of correlation in book, but I am giving one of them. So, this is, but remember that sometimes you will find these correlations, sometimes is based on the measured n value, sometimes it is based on the corrected n value, sometimes with some corrections you have to apply, some are not. So, based on that you have to use those corrections. So, you have to be very careful when you have to use the corrected n value, when you have to use the measured n value, when you have to use the some correction, some are not. So, for example, this is n dash 60, but here overburden correction is not applied. So, this correlation is based on that. So, if it is 0 to 2, that means Cu value 0 to 12.5 kPa, it is very soft. Similarly, if it is n value is greater than 30, it is hard soil. So, these are the some corrections and visual identification also you will get. Similarly, for the this is for the clay, this table. Similarly, for the granular soil also you will get. Again, this is correction, this corrected n value, but correction is not applied for overburden pressure. So, this is from 0 to 4 is very loose, then greater than 50 is very dense, 30 to 50 is dense, and corresponding relative density RD is the relative density also you will get for granular soil. Next, I will go for the cone penetration test. Previous one, the standard penetration test and the cone penetration test. It has two types. One is dynamic cone penetration test, another is the static cone penetration test. So, in the dynamic cone penetration test is similar to SPT. It is also hammer driven and using cone, but the difference of dynamic cone penetration test with SPT is that in SPT we use the split put sampler, but here we use the cone. So, in SPT we can collect the soil sample, but here we cannot. So, again the blow counts are given at a interval of 1.5 meters, and then for the static cone penetration test, so it is pushed, it is not the hammer driven like SPT or DCPT, it is pushed into the ground at 1 centimeter per second, and it gives continuous reading. SPT also give readings with certain intervals, 1 meter or 1.5 meters. DCPT also give in readings certain intervals, 1.5 meter, but the SCPT gives the reading which is continuous. And remember that in SPT we need boreholes, but in cone penetration test CPT boreholes are not required, because it is either pushed or driven into the soil. So, the static cone penetration test, so this is the IS code for this test is 4968 part 3 1976. So, the equipment those are used here, the steel cone, then friction jacket, sounding rod, this is the sounding rod, and driving mechanism and measuring equipments. The angle, this cone angle is 60 degrees plus plus minus 15 minutes, and overall base diameter is 35.7 millimeter with a cross section of 10 centimeter square. Okay. And this friction jacket friction slab, or this slab outside area is 150 square centimeter. The sounding rod is this sounding rod is a 15 millimeter diameter. Generally this length is 1 meter each, but we can extend the length of this or length of this cone by attaching additional rods of 1 millimeter each, as I mentioned. So, this is the rod, you can attach another one, and then you can put your you can go up to the required depth. So, the driving mechanism should have a capacity of 20 to 30 kilonewton for manually operated equipment and 100 kilonewton for mechanically operated equipment. So, this is the static cone penetration test. Here we are not applying any blows. The driving equipment, it will push it into the soil. So, now I will show you by this animation how these things works. So, this is the total assembly of this static cone penetration test. This is the sounding rod, this is the mental tube, this yellow one, the friction jacket, this black one is the friction jacket, and the cone assembly is this one. Okay. Now, first this sounding rod along with cone assembly is pushed by 40 millimeter into the soil. So, sounding rod, so you can see the sounding rod along with cone assembly is pushed into the soil by 40 millimeter. So, by which we will get a resistance. So, that resistance will give me the cone resistance, which is known as a QC. So, this resistance will give you the cone resistance, which is QC. So, this stage the resistance that I will get is the cone resistance, which is QC. Now, the next step, this is the same stage. The next stage, the sounding rod, the cone assembly and the friction jacket all are pushed into the soil by 40 millimeter. So, initially the sounding rod and the cone assembly is pushed into the soil by 40 millimeter. Now, the sounding rod, cone assembly and the friction jacket are pushed into the soil by 40 millimeter. So, in the second stage, the resistance that I will get is the total resistance. That means, the cone resistance plus friction resistance. So, this will be the total resistance. Now, if I subtract the cone resistance from the total resistance, then I will get the friction resistance. So, clear? So, this test I will give you the cone resistance and the friction resistance separately. First stage will give you the cone resistance, second stage will give you the friction resistance plus cone resistance, that means the total resistance. In the third stage, what I will do, that this mental tube is pushed into the soil by 40 millimeter, and in the fourth stage the mental tube along with the friction jacket is pushed into the soil another 40 millimeter. So, remember that the first two stages are required to measure the resistance, but the second two stages are required to bring back this instrument in its original position. So, one question may come that the first second stage also we push the friction jacket, fourth stage also we push the friction jacket. Why? The first stage friction jacket is pushed to measure the resistance, but the fourth stage friction jacket is pushed to bring the instrument into the original position. The fourth stage will give you the original position. Okay? So, that means the first two stages are to apply the to use to measure the resistance, and third and fourth stages are used to bring back the instrument into original position. Okay? After doing the SPT and the CPT static cone penetration test, finally we will get this type of data. So, this is the SPT blow count with depth, S1, S2 are two different bore holes, and this is the SPT cone resistance, only cone resistance along with the depth for two different bore holes C1 and C2, and we can identify the soil also, because by SPT we can bring the soil or the by N value also we can identify soil. So, this is the soil type, and this is the cone resistance, and this is the SPT value. So, once you will get this cone resistance and the friction resistance, then we will use the correlations, okay, like SPT also, and this we use the correlations, and then for the because all the SPT, CPT or other cone penetration test and other field tests, there are number of correlations are available, but I am giving few of them. Okay. So, for the clay we can determine the undrained shear strength or undrained cohesion by using QC minus sigma V Nk. What is QC? QC is the cone resistance that I will get from the first stage, and then sigma V is the total vertical stress or total vertical overburden pressure, total not effective, total vertical overburden pressure, and Nk is the cone factor. So, if you use the electric cone, then it will be 15, if you use the mechanical cone it will be 20. So, if we put these values we will get the Cu. Similarly, for the sand also we can get the friction angle, and that is the equation, and here this is sigma V bar, that means the effective vertical overburden pressure, and here it is sigma, this is total, this is effective, and this is again the QC, that is the cone resistance, and this is the expressions we can use for the clay and the sand to get the strength parameter. Then we can use these CPT for the clay soil to determine the pre-consolidation pressure. So, what is pre-consolidation pressure? That means we know the soil may be normally consolidated or the over consolidated, and if the soil current stress is more than the stress which soil already been experienced, then this is called the over consolidated soil, and this is called the normally consolidated soil, and if the current stress is less than the stress that soil already been experienced, then that is called the over consolidated soil. So, the pre-consolidation pressure is the PC, that means the stress which soil already been experienced. So, now if your current stress is more than PC, then we can say the soil is normally consolidated. That means the current stress that soil is experiencing is more than the stress that soil has already been experienced. So, that stress is PC. So, now the soil stress is more than PC. So, it is normally consolidated, but if the stress is less than PC, that the current stress is less than PC, then the soil is called the over consolidated stress, because the previous stress was more than the current stress. So, that PC value is very important to identify, because based on that we can identify whether soil current state is over consolidated state or the normally consolidated state. So, if the PC value expression we can get by PC value we can get by using this expression. So, here QC is the cone resistance and we can over consolidated ratio also we can get by using this expression. Sigma V is the total vertical overburden pressure and sigma V bar is the effective vertical overburden pressure. And for as you know, for the normally consolidated stress, normally consolidated soil, we generally consider the OCR value is equal to 1 and over consolidated soil OCR value is greater than 1. So, this is your OCR also you will get from the cone resistance. And we have different charts also by which also we can determine that soil relative density or the friction angle. So, this is for the sand. If I know the cone resistance, if I know the vertical effective stress or vertical overburden pressure. So, we know this value and the cone resistance, then we will get the relative density of the soil and we will get the different friction angle of the soil also. Then if I know the friction ratio is the ratio between the friction resistance or the slip friction and the cone resistance or the tip resistance. Sometimes it is called tip resistance also. Tip resistance QC by Fs. Fs is the friction resistance or friction or the slip friction. So, if I get this ratio Fr and then if I know the cone resistance QC and the friction ratio Fr, then we can identify which type of soil it is. Okay? So, that means it can be clay, it can be clay silt or silty clay, sandy silt, silty sand, sand. So, if it is in this zone friction ratio and the cone resistance, then it will be sand. So, this way we can identify the soil also. Now, modern static cone test, the pore pressure can also be measured. So, here we can also the cone resistance, friction resistance we can measure, as well as the same time we can measure the pore pressure also by using modern static cone penetration, by using modern static cone penetration test or this piezo cone, which is called the piezo cone. Now, next one is the dynamic cone penetration test, where in the static cone penetration test it is pushed into the soil, but here it is inserted into the soil by hammer blow, which is similar to the SPT. So, here also the hammer blow, weight is 65 kg and which with a free fall of 750 millimeter and number of blows required for every 100 millimeter penetration is recorded. Okay? And this process is repeated up to the required depth. And the difference, the major difference, as I mentioned, that in the SPT we can collect the soil sample, we use the split spoon sampler, but the DCPT we use the cone, so we cannot collect the soil sample. So, this DCPT is better than SPT and SCPT, static cone penetration test, in hard soil such as dense gravels. And like SPT also we can put correlation for this blow count with different soil properties. So, this is the cone penetration test. So, in the next class I will discuss about the other different these soil exploration methodologies by which also we can get the some parameter which will be correlated with different soil parameters. Thank you.